Here's my constant velocity motion lab. Let's get started. Constant velocity is where an object moves at a constant speed with a specific direction. Since it has a magnitude and direction, it is a vector velocity, that is. If an object moving at a constant velocity, then it has no acceleration, and if there's no acceleration, then the net force has to be equal to 0, as shown above. At this point, I'd like to mention that acceleration and force are also vectors, as indicated by the harpoons above them. Although net force might be equal to 0, there still can be forces acting on the ball, like normal force, force of friction, force of gravity, as shown below, but the net force would be equal to 0 because they would cancel out. Some other important equations are the velocity function and the position function, shown right here, and they're both derived from Newton's second law and are used in the code. So the video we tracked was a ball moving across a screen, and we brought it into tracker right here. Now we found the diameter of the ball by taking the circumference and dividing by pi, and it was 22 centimeters, or 0.22 meters. And then we tracked the ball across the screen right here, and if you look in the upper right hand of the screen, you can see the graph that was created from the tracking points. It looks pretty linear, which is a good sign. Now here's the data right here. Alright, great. And notice here that the frame rate was 60 frames per second, and the delta t was Now we get to the key points. It's just really a review of the video. Pretty much the same thing, just remember the start point was 0 at time and position, and the end point was time 0.567 and position 1.05. And from the small delta t right here, we were able to determine that the velocity was 1.71 meters per second in positive x direction. We took that information and created a model with it. Here you can see that the mass of the ball was 0.45 kilograms, although that wasn't really important. The ball's position was 0 at the beginning, and the velocity at the beginning was 1.71 meters per second as well. And here also the delta t, same as in the video for the model, it was 0.017 seconds. And for the calculation loop, the time went all the way up to 0.567. Now notice here that the equation right here is the same one as the velocity function. The only really important thing is though the velocity function depends on the net force, and the net force is equal to 0 because it's constant velocity, so there's no acceleration, so net force is equal to 0. Now that's the position formula, which was also important. It's used to determine the new position of the ball, and that's delta t. Now we go to run the actual operation, or the module, and the ball successfully moves across the screen, and also a graph is generated, linear as well. And now we go up to the data. As you can see, since the experiment and model both have the same delta t, we can nicely put them together. And also look at the endpoints. They are slightly different, so there's a little bit of a discrepancy there. Here's the results. As you can see, the model position was slightly below the experimental position. I'm not sure why that was. It seems as though the original delta t, the small delta t that we took for the beginning to determine the model's velocity, initial velocity, was a little bit off. It seems that the actual experimental velocity should have been a little bit greater, which is why it's above. Although normally we would determine, or we would think that the experimental should have been below because of friction. But yeah, so we found about 8% error with the two slopes, which isn't too bad, although it would be magnified over a larger time scale. Anyway, thanks for your time. Please leave some constructive criticism and have a nice day.